Consider the circuit network shown here, and the objective is to find the Thevenin equivalent across AB. So how do we go about finding the Thevenin equivalent across these two nodes AB? So the first, we need to find the Thevenin impedance ZTH or RTH, and next the Thevenin voltage. So what are the steps? So find the Thevenin impedance. So for that, you do the following. Keep AB open circuited, then short all voltage sources in the network. So here V1 and V2 should be shorted. Next, open all current sources. All current sources should be open circuited. Here there are no current sources, so therefore it does not apply for us here. And then redraw the circuit. So if you redraw the circuit, it will appear like this: 8 ohms, 25 ohms, 4 ohms, 10 ohms and 10 ohms. Now we need to find out what is the equivalent impedance as seen by a person in this direction through the terminal A and B. So what is the impedance seen in this direction, seeing through the terminal AB? So it has two parts. There is one 10 ohm part here and all these parts. So these two are in series. So let us simplify this part first. So this can be considered as 8 ohm, 25 ohm parallel in series with 4 ohms and then a 10 ohm there. Now this portion of the circuit can easily be simplified. These two are parallel, therefore you take product divided by the sum. 25 into 8 divided by 25 plus 8. So this is approximately 6. So this 6 in series with 4 will be a 10. So this 10 comes in parallel with another 10. So this can be written like this. You have a 10 ohm in parallel with 10 ohm, which will result in a equivalent 5 ohms coming across this terminal at these 2 points. So we can draw this taking this and this into account. So you have a 10 ohm and a 5 ohm which comes across the AB terminals seen from this angle. So this is 10 ohm and this is 5 ohm. So totally you get 15 ohms. The Z Thevenin or the R Thevenin in this case, because it's only resistance, is 15 ohms. So this is the Thevenin impedance. Next we have to find the Thevenin voltage. So for that, consider source V1 only and short V2. Find VAB. We call that one as value 1. Next, consider only source V2 and short V1. Find VAB and let that be equation 2, value 2. And by superposition theorem, you add 1 and 2 to get the Thevenin voltage. So here the concept is that you have to take one source at a time. So when you take one source, you have to short all other voltage sources, open all other current sources. So that is the concept. So considering our circuit, now with V1 and V2 shorted, it will look something like this. V1 10 volts, all other parameters shown here like this, and you have AB. We need to find VAB. Let me mark C and D as shown. VCB is the voltage from this point to this point, or this point to this point. You can call it VC also. VC is same as VAB because there is no current flow here. AB is open circuited, and therefore the voltage drop across this is 0. So therefore we can say VCB is same as VAB, and then we can calculate what is the voltage across this, because this is providing 0 voltage drop, no current flow through this. So you take just this portion of the circuit. So let us find out first what VD node voltage is. So we have 10 volts, 8 ohms, and all these resistances equivalently will be put in here. And this is this in series with this. This is out of the picture. So 4 in series with 10, and that combination in parallel with 25. So 25 ohms parallel with 4 plus 10, which is 25 into 14 divided by 25 plus 14, product by sum. And this approximately works out to be around 9 ohms. So this is a 9 ohm resistance. And if you have to find VD, it is nothing but by the voltage divider rule. You have VD equals 10 into 9 divided by 9 plus 8, and that will be around 5.2 volts. And to find VC, this is VD. VC, again use the voltage divider rule. VC equals VD into 10 divided by 10 plus 4, which is 5.2 divided by 10 by 14, and that is 3.7 volts. Now this is value 1, as we mentioned here, value 1 of the VAB, and store it apart, store it aside. Now consider the other source, V2. So we are using the V2 8 volt source now, and V1 the 10 volt source is shorted. Now for this, let us perform the evaluation of the voltage at VC. So the circuit, these two will come in parallel, so 8 and 25 ohms in parallel, and then you have the 8 volt source coming in here, 4 ohm and 10 ohm coming in here, shown like this. So let us number them. Now this 2 is in parallel, so it is product by sum, 8 into 25 by 8 plus 25, approximately 6 ohms, that is this. So the circuit translates into this, where you have, this is 10 ohm, this is 4 ohms, this is 6 ohm, and you can interchange the position of 8, and because they are all in series elements can be interchanged in position without affecting the operation. So you have 8 volts, 6 and 10 will combine to form 10 ohms, and the voltage at VC is applying the voltage divide rule, 8 into 10 divided by 10 plus 10, which is 4 volts. So the second value is 4 volts. Now we can apply the superposition theorem and find out Thevenin's voltage, which is 1 plus 2, which is 3.7 volts plus 4 volts, which is 7.7 volts. So this is a Thevenin voltage. We have found out the Thevenin impedance, Thevenin resistance, and also the Thevenin voltage. Now the equivalent circuit is something like this. So let us draw the equivalent Thevenin source. This is the equivalent Thevenin series impedance, or the driving point impedance. This is the terminals A and B. So V Thevenin we calculated at 7.7 volts, R Thevenin calculated as 15 ohms, and this whole thing is the Thevenin equivalent. So Thevenin equivalent circuit. For the given circuit, this is the initial circuit we started off with. This was the given circuit. For this circuit we have found the Thevenin equivalent. So this whole portion of this network, the fixed portion of this network, is replaced with V Thevenin and R Thevenin and brought out to the terminals A and B.